Hello people, Zach here again today, and this video is going to be a response to a recent video uploaded by Sabine Hossenfelder, probably about 4 or 5 hours ago, I think, regarding gravity not being a force. So in her particular video, she was talking about using springs as accelerometers and like tying the head end of a spring to a rocket, and the rocket accelerates, and it creates like causes the spring to expand in a certain direction. You can sort of tell that there was an acceleration applied to the spring, but then she starts showing this like an example of someone holding an accelerometer in their hand, and the accelerometer says that there's an upward force on the object, and she's sort of saying that's like a proof that gravity is not a force, that actually the force is coming from your hand pushing up. And so I'm just going to go ahead and refute this because, like, if you've watched my content at all, you know for sure that I don't agree with the idea that gravity is space-time curvature. I think the whole idea is kind of ridiculous. So let's go ahead and get into this. So for considering a spring, we can think about 5 different particular states. One is the non-accelerating state, which we call state 0. And in this particular state, the length of the spring is going to be equal to its neutral length, and the density at the head end is going to be equivalent to the density at the tail end. So it's uniform throughout the entire thing. Now, this second state, which is our state 1, is going to be what happens when the head accelerates outwards from the center of the spring. And so like you see here is that you have less density of the coils on this end than there are on this end. So the length is increased, length is greater than length sub 0, but the head density is lower than the tail density. Third case is where the tail end of the spring is accelerating outwards, in which case we see that, the inverse is also true now, where the length has increased, but the density of the head end is now higher than the density of the tail end. And now we get to state 4, which is where the head end is being accelerated inwards into the spring. And in this particular case, the density of the head end is increasing while the density of the tail end remains the same. So you have a higher head density than tail density. And then, of course, our last one, which is our state 4, is where the tail end is accelerating inwards into the center of the spring, in which case you have a high density on the tail end and a low density on the head end. So the head density is lower than the tail density. So these are the 5 different states that you can tell that the spring is in, and sort of tell which way, well, I guess more or less which end of the spring is accelerating and in which direction. So this part, I don't think would anyone have a problem disagreeing with, and I don't disagree with this at all. It makes perfect sense to me. So the next part we're talking about here has to do with the pinning of the head and tail of the spring. So we can think of 2 different situations. Situation A is where we have a spring where we've pinned or anchored the head end up into the air. And this is going to lead us to a situation, like if you've ever hung a spring, you notice that the spring actually expands. Like it gets longer. So this means that we have to deal with a situation that's either S1 or S2, because those are the only 2 situations where the length is going to be greater than the length at the neutral state. So the second situation, which is situation B, is where we're anchored at the ground, where you actually have it sitting on a surface. And in this case, the spring will actually contract if it's a compression spring. So if it's a type of spring that's built to be able to contract, it's going to contract. And then for this course means that we're going to have a situation of either S3 or S4. So now we get to the next stage here. We'll consider more about what's going on. Situation A is actually, more specifically, is going to be S1. And the reason why this is the case is that if you have a spring and it's dangling by an anchor here, you have more of the mass of the spring below that anchor point, and the amount of mass that is below any particular point decreases the further you go down. So like if you're up here, you have a whole lot of mass, the whole mass of the spring down here. But if you start here, you have less of the mass below that point. If you start here, you have less of the mass below that point. So it diminishes more and more. And so this is the reason why you have more of displacement here than you do here. And so this right here is a second situation, which is it's sitting on a surface. And this is equivalent to the thing she was talking about before, where you have the accelerometer held in your hand. And I'd say that this is an S4 situation, because the spring is actually going to be more compressed near the bottom than near the top. And the reason why this is the case, we can get by looking at, of course, at the mass here. So obviously the mass of the spring that's at part M1 is going to be less than the mass of this of the part of the spring that's at M2. And the reason why this is the case, of course, is because you have a higher density at M2 than you have at M1. But what's more important than this is actually this relationship right here, where you have M3, M4, and M5. So obviously M3 is greater than M4, which is greater than M5. And the reason why this is more significant is when we start getting this situation right here, which is the neutral spring. So if we assume that this spring was actually neutral sitting on the surface, like it wasn't compressed at all, well, M1 would equal M2 in this situation because the density is the same throughout the entire spring, but this relationship would still hold true. This M3 greater than M4 greater than M5. And why that relationship is important comes from this right here. If Mf is equal to Ma, then the force is proportional to the mass. And of course, the force of gravity for the mass for section 3 is going to be greater than the force of gravity for the mass at section 4, which is going to be greater than the force for gravity of the mass at section 5, because there's less mass at 5 than there is at 4, and there's less mass at 4 than there is at 3. And of course, if we apply Hooke's law for the spring, F sub s is equal to negative k delta x, we can rearrange this equation and see that delta x is equal to negative Fs over k, in which case we can see that the displacement that should occur at F3, like the degree to which it displaces, should be greater than the displacement for the section at G4, which should be greater than the displacement for the section at G5, which is what we see with B up here. So what does this actually mean? What this means is that although it is true that this S4 situation that we're seeing right here corresponds to having the tail end accelerate up, where you're applying a force from the bottom of the spring, we also still cannot tell the difference between that and a force that's being applied to all of the mass of the spring that is downwards. You cannot tell the difference. Well, with the exception of the fact that you can tell when something is accelerating with your eyes, as opposed to gravity, I mean the way the general relativity explains it, where it's an invisible curvature of space-time that you're just supposed to trust on faith, is the case. So that's my argument. I hope you found it interesting. Thanks for watching.